Here in part B, we're going to go back to the example that we just did, but in this case, we're going to keep M and K fixed, and we're going to vary the damping parameter of C to see what root locus that we get. Now, in order to put that in our form of the closed loop transfer function, the denominator of that, in this case, we divide through by ms squared plus k, and that puts our closed loop transfer function looking like this. This is what we're calling n over d, like that. And so if we go through our rules, we see in this case our d is quadratic, so we have two poles. Our numerator is a linear function of s, so we have 1 as 0. We look at the maximum of np and nz, that's 2. And again, it's no surprise that we have two branches, because that's what rule number 1 says, but we already knew that because our transfer function is second order. If we look at our open loop zeros, the zeros of n, we have 1, as we said, that 1 0 is a 0. Our open loop poles, that is the roots of d equal to a 0, we have two of them, p1 and p2, are plus or minus 2j. So if we go back to our basic fundamentals here, we know that our root locus plots start at the poles, so they start at p1 and p2. The root locus plots end at either the zeros or at infinity. We got 1 as 0, z1, and so therefore the other one must end at infinity. So let's look at rule 4. In this case, in fact, let me scroll down to our plot here. And I'm going to draw in what we know. We know that we have these two poles on the imaginary axis at plus or minus 2j. And we have these 0 here at the origin. So recall that what rule 4 says is that any region to the left of an odd number of open loop zeros or poles must be part of the root locus. So what we can say right away is everything over here on the left hand side, real axis, is somewhere at some point part of the root locus. So let me write that down in words. Then that's all of the negative real axis is part of the root locus. If we look at rule 6, looking at, in fact, let me remind ourselves of what rule 6 is. It's the breakaway reentry points. And rule 6 says that we find these by setting the derivative of n over d with respect to s, setting that equal to a 0. So this is the derivative for this case, n over d is s divided by 2s squared plus 8. We recall how to take the derivative of a quotient. We take the derivative of the numerator n, that's a 1, multiply it by d. We subtract away n, which is s, times the derivative of d, so that's 4s, and divide by the square of the denominator d. And since rule 6 says that we set this equal to a 0, what we get back from this is an equation which governs our breakaway reentry points. Minus 2s squared plus 8 equal to a 0. So it says that this occurs when s is equal to a minus 2. That's pretty much all that we need. Let me include that. The minus 2 line, I'll draw that in here. Like that. So the rules say that we start at our open loop poles. That represents the root locus for C equal to a 0. They enter the real axis here at minus 2. So that one comes in from the top. This one comes in from the bottom at a 90-degree angle. And once they hit, then they split. And we see that all this is abiding by Rule 4, which says that everything to the left here of the origin on the real axis is part of the root locus. So it ends up C equal to infinity at the origin, and C going to infinity goes out to infinity on the real axis. So again, this is an application of rules 2, 4, and 6, which gives us that. Well, this is in agreement with what we've seen before. Recall that for a second order system, if we keep the natural frequency a constant, in this case that's represented by K over M, then the root locus, when it's complex, is a circle of radius omega n, which is square root of K over M. So this is in perfect agreement with what we've seen by solving the quadratic equation exactly, but it's a good way to exercise our skills here in drawing root locus plots.